All right, everyone. So let's begin today's session. So the for the YouTube link for this session is in the chat. Ma'am has put that. Okay. So today we'll start with week two. So week two starts with continuing the determinant part. So if you have any doubts regarding determinants so far, what we saw in the previous week, week one, you can ask that now, and then we'll proceed to the week three part of determinants. So, does anyone have any doubts with determinants or week one?
Ma'am, week
Yeah,
3 is not released yet. So how you can?
week two, week two.
Okay, sorry. Yes, ma'am.
Yeah, 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 Bhavna.
Actually, ma'am, I have a doubt from activity 1.5.
Okay. What is your doubt? Like, what is the topic? Determinants only.
Yes, ma'am.
Okay, let me see that. Which question?
Ma'am, 10th question.
1 second. Okay, is my screen visible?
Yes.
Yes, ma'am.
Okay. So, 10th question. All right. So it says that A and B are two 3 cross 3 matrices, okay, such that determinant of A is 4 and B is equal to 3A. Find the value of determinant of A square, the third root of this. Okay, so what is your doubt here? Like the computation, how to calculate it?
Yes, ma'am.
Okay, so this, like you can take a third root of it because it's a real number. Okay, so determinant of a square b means you have to perform matrix multiplication. So how do you get a square? You multiply this thing by itself, but they haven't given us the actual matrices. So what you have to do is use the properties of determinants. So the properties of determinants, the first one, that is what we'll begin with today. This is a good intro to our week two contents because the properties of determinants is what we start with. So I'll just go to that, and the first property only deals with this. Okay. So I'll just share my note screen now so that we can just directly go to the properties because the first property is going to deal with this determinant properties. Okay. So 1 second. All right, I'll just share my full screen. Let me know when you can see my note screen. Okay, 1 second. Okay, is it visible?
Yes,
Yes.
ma'am.
Okay, so the first property is that the determinant of a product is the product of the determinant. So if you have determinant of AB, then that is equal to determinant of A times determinant of B. Okay, and also you can take it in any order. So determinant of AB is equal to determinant of the product of BA also. That is also there. So normally when we see two matrices, suppose we have a matrix A, it's 3 cross 3, and we have a matrix B that is also 3 cross 3. Okay. So we take the product of these two matrices, suppose because we can take the multiplication, right? So like, can anyone tell me to multiply two matrices? Like we have some criteria. So what is the valid criteria? Can anyone tell me?
Number of
Number of
columns of the
row,
first matrix
number
must
of
be
columns
equal
of
to
matrix
number
A
of
is
rows
equal
in the
to
second
number of
matrix.
row of
Yeah,
column matrix
correct.
B.
Yeah, so these two should match. That is the only criteria. And then the product has these two. So we can take A, B as well as B, A, because these two match, and also these two match. Okay. So because if we're taking B, A, then also it matches. So, but there's this thing. A, B is not equal to B, A necessarily. They can be different matrices. However, when we have determinants, the determinant of AB is equal to the determinant of BM. Okay, that is one thing. And also, the determinant of the product is equal to just taking the determinant of A separately and the determinant of B separately and then getting it. So, in the given question, if we open that again, we have here that determinant of A is 4 and determinant of B is 3A. Okay, so that means B is 3A means what? What is the determinant of B? Can anyone tell me?
3 times the determinant of A.
Are you sure?
8 times, sorry,
Ma'am, K power
27
n
times.
3 raised to 3.
Times.
determinant of
Yeah.
A.
So what is happening is another determinant property is that if like each row that you multiply by a number, the determinant gets multiplied by that number. So we have a matrix A. Okay, let's take it's the identity matrix. Okay. So suppose we have 1 0 0 0 1 0 0 0 1. This which is actually I, you just directly write I. Okay. So suppose I have 3I. Okay. So what is happening then? So we are taking 3I. So what is this matrix now? One second, I'll just share this again. Sorry, screen issue. Okay, so is it visible now?
Yes, ma'am.
Yes,
Yeah,
ma'am.
Yes,
sorry,
ma'am.
this part didn't come on. So I is the matrix we have. Okay, so now we're taking 3I. Okay, so what is this matrix?
3 0
Yeah,
0 0
so
3
every
0
single
0.
row is being multiplied by 3. 0 3 0 0 0 3. Okay, so let's calculate the determinant of I. What is it? So determinant of I is equal to, so we'll take 1 first and then 1 multiplied by this whole thing. So that is going to be 1 into 1 and then 0 into 0 minus 0 into 0. So that's just 1. That is equal to 1. Okay. So now if we take this determinant of this one, let's compute that. Determinant of 3I. Okay. So now we have to take 3 and then we are taking 3 into 3 minus 0 again. So that is 9. So this is 27. So what we see here is that the determinant became 3 raised to whatever number of rows you have. So the dimension, the order of the matrix matters. You can't just directly say 3, like if determinant of A is 4, then the determinant of B, if B is 3A, then it won't be 4. It is going to be what then? It's a 3 cross 3 matrix. So they've said that determinant of A is equal to 4. Okay. AQ 1.5, question number 10. Okay, they've given this. Okay. And they're saying B is equal to 3A. So what is the determinant of B? Just based on this, what? Yeah, because what we're doing is 3 and they've said A is a 3 cross 3 matrix, right? So that means you have to raise 3, it's 3 into A, so 3 is being raised by the order. So if it was 2 cross 2, then it would be 3 raised to 2. So here it's 3 raised to 3. That is what we have to multiply by the determinant times determinant of A. That is this thing. So now we have 27 into 4 and that is equal to 108. Okay, so now we have both the values. So for what they've asked, the third root of determinant of A square B. So how would we compute this? Anyone?
Ma'am, you can write
Ma'am,
it.
determinant of A whole square into determinant of B. And
Yeah,
I mean, what is inside the root for that? I'm
yeah.
trying.
So now this is happening. So now the first property that we saw is coming into effect. So determinant of A is okay. We have to split it out into individual determinants. That's what's going to make it easy for us. Okay. So we'll just simplify this for us as much as possible. So what we'll do is we'll rewrite determinant. We'll forget the third root now. Okay. So determinant of a square b, that we'll split it out. So applying the first determinant property here. So this is determinant of a times determinant of a, because a square, and then determinant of b. One second. All right. So now we have computed all these values, right? So this is going to be 4 into 4 into, what is it?
108.
Yeah.
One.
108.
Yeah. So 27 into 408. So this value, and the question is asking for the third root of it. So we'll just take that, okay, cube root, and then this thing. So you have to just calculate this. That is all you have to do. Is it clear?
Yes, ma'am.
Okay. So that was that doubt. So this is like the first property of determinants. Properties. Okay. Okay. Sitara, your doubt. Bhavna, is it clear?
Ma'am, I
Yes,
have
ma'am,
a
it's clear
doubt
now.
from week
Thank you,
two.
ma'am.
Okay. Yeah. Yes, Sitara.
Not, ma'am, I have a other question that is from week two.
Yeah, we're doing week 2 only. So we are starting off the determinants now. So I'll just proceed. Which topic is your doubt in?
Ma'am, it's an activity question.
Okay, okay, we'll get to that. We'll go through all of them. I'll go through the determinants. Like first lecture is determinants part 3, right? So I'm just going through the properties. If you have any doubts, you ask. Then the activity we'll deal with. We have 2 sessions. So because there's a lot of content, after this we'll go to Kramer's rule and all that. So we'll not. The goal is not to finish all of it today, but we'll do as much as possible. And in this, we'll take any doubts. And at the end, if we have time, we'll take other doubts also. Okay? Yeah, Disha.
Okay, okay.
Yeah.
Ma'am, I have a doubt in 1.5 activity, question number 7, in last
Okay.
second option.
Okay, this one, determinant of A is 6.
Yes, ma'am.
Okay, so what is your doubt here?
Ma'am, in this, we are going to finding determinant, then it's all places are J, then how I can calculate determinant for this?
So the it's like IJ. Okay, so IJ basically means that the particular position. So I'll just take this also in my note. One second. Okay, is it visible? The note is visible.
Yes, ma'am.
Yeah. So what this means is like IJ. Okay, so each position of a matrix has like this, it's assigned this value so we can locate it. Okay, so if we have matrix A, all right, so we'll call this part, this entry is the 1 1 at entry. So 1 1, and this is 1 2, this is 1 3. Why? Because 1 is the first value, because this is the first row, and the second value corresponds with, so I basically corresponds with the row number, and J corresponds with the column number. So similarly, you will have 2 1, A 2 2, yeah, you got it. So end mein you will have A 3 3. All right. So that is what you have. So the question is asking, so how is it calculating the determinant? So A is this matrix. Okay, so we'll first set up this matrix. I'll just put this 1 second. I'll take a screenshot and add it to my this thing. Okay, 1 second. Okay, there's some issue. I'll just try and get it. Give me 1 minute. Okay, got it. Okay, so this is what it says. So A is equal to this matrix. Okay. So here, if I is greater than J, then the entry is going to be 0. So you have to first, this is question number 7, right?
Yes, ma'am.
Yeah, I'll just, yeah. So So if I is greater than j, that means the row's number is greater than the column's number, then that particular entry is going to become 0. And if I is less than or equal to j, then we'll set whatever the j value is. So let's do that with this. Okay. So here is I greater than j. I is 1, j is 1. So let's set up this matrix here. Okay. So you know how to, like, what is I, what is j? I is the row number, j is the column number. Okay. So let's set up this matrix now. So tell me, what will be the first entry? I, j is 1, 1.
1J.
One.
Yeah.
I'm
So
one.
it's just 1 because they're saying the entry is just j if I is less than equal to j. So in 1, 1, it's equal to, so it's just the column number is 1. Okay. The next one is 1, 2. So what is the entry here? This entry.
Two.
Is it 2?
2. Yes, yes,
Okay.
ma'am, 2.
Yeah. Because again, I is 1, j is 2. If I is only greater than j, then it's going to be 0. It's not greater. So it's 2 because they're saying it's going to be j directly. Okay. Now the third one is similarly 3. Okay. Now here, what is this entry? The 2, 1 is
0.
entry.
0.
Zero.
0. Yeah, because now I
0.
is greater than j. Yeah. It's going to be 0. Here it's 2, 2, right? So it's going to be 2.
Two.
And here 3 again. Okay, and here it's going to be like, now I think the pattern is clear because 3, 1, so I is greater than j, 0. 3, 2, I is greater than j, 0. And then 3, 3, it's equal, so 3. So this is your matrix. Now based on this, you have to calculate the determinant. Okay.
Okay, ma'am. Yes,
Yeah.
ma'am.
So now, any other doubts from, okay, Aditya?
Yes, ma'am.
Yeah, you raised your hand. So you have any doubts from week 1 on determinants or something? No doubts? Okay, so we are going with determinants. If you have doubts on determinants, I'll just start up with week 2 now. Okay, then we'll take more doubts later. So week 1, right now I'm pausing because we do need to start week 2. Okay, so I'm starting with the determinant properties now. All right. So week 1.5 we took some because that is determinants part 2. Now we're going to the determinants part 3. Okay, so let's begin. So this is what we're going to now. So here is determinants part 3. So this is
Ma'am,
what,
am I audible?
sorry, you're not audible.
Excuse me, ma'am. My power went off. Am I audible now?
Yeah, you're audible now.
Hello, ma'am.
Yeah, you're audible.
Yeah.
Hello?
So this practice assignment one, question number two, the last option I can.
Which one? Which activity?
Practice assignment one, question number two, the last option.
Okay, we'll deal with practice
Hello,
assignment
ma'am.
later. Okay, we'll deal with practice assignment later. I am
Ma'am, practice assignment one, question number two.
okay, we'll deal with it later because now there are many determinant related concepts to go through. And practice assignment, it's for week 1, so that covers mainly week 1 concepts, right? So I'll just begin with week 2. But if any determinant related doubt from the lectures, like the last 2 lectures, I can take one more because we are going to cover that again. You have to do Kramer's rule also. So any determinant related doubts? Yeah, Ripusudan Kumar Jha, you are next in queue. If anyone has determinant related doubts, I'll take those.
Ma'am, I have doubt in the activity 2.4 question number 10.
Okay, we'll come to that when we get to that part. We'll go in like, sequence. Okay, so I'll just proceed now.
Okay,
You
ma'am.
can raise your hand and we'll go. I'll pause at after like every concept, I'm going to pause and I'll ask for doubts also. So maybe like we'll clear it before we can get to you also. Okay, so let's begin now. So we covered 2 properties of determinant so far. So also on discourse, we have this Pulkit's post session like math 2 resources by TA. So in that you can find this note. I actually type up the properties and put it more neatly. I thought it would be like more, easier for understanding if we did everything together. So this is the first property of determinants. Okay. So a determinant of a product is a product of determinants. Then we have property number 2. Okay, if that switching two rows or two columns changes the sign of determinants. These are determinant properties. So switching rows or columns changes the sign of the determinant. Okay, so anyone, let's take an example 2 cross 2 determinant for like quick computation. So you guys give me a, like, let's make up a matrix now. So I'll take, it has to be 2 cross 2. Okay, so give me any value. We'll make a matrix and we'll do all the, like, all the properties we'll test on this. So let's take A and B so we can try it out. So give me any number.
Ma'am,
1,
1,
2, 3,
2,
4.
3, 4.
1, 2, 3, 4. Some different. 3, 4 is going to be, let's take
7,
5,
7.
9, 5, 7. Okay, let's take 5, 7. Okay, okay. Another one. Let's make up something different now.
8, 9, 3, 4.
9,
It's 8.
9, 3, 4.
Okay, nice. Okay, so we have these. Okay, so the second property is that switching to rows or columns changes the sign. So let's just do with A now. So let's compute the determinant of A. Okay, so what is the determinant? It's like we've been through this. We'll multiply this by this and then subtract this. Yeah, 7 minus 3.
3.
We'll just do that. Okay, now let's switch it up. So let's do, we'll switch the rows first. So let's do A star is equal to 5, 7, 1, 2. Okay, and determinant of this is, now you can clearly see that is 10 minus 7, so 3. So now here you have minus 3, here you have 3. So property is there. Also, another thing is that every someone please mute yourself. One second. Yeah, thank you. Okay. So here, and also what I was saying is, I'll take a 3 cross 3 example now just to show that every single switch is going to change the sign again. So suppose we have, say, I'll take the identity again just for simplicity. So I is here, okay.
Ma'am, your audio is
Ma'am,
Voice,
you are not
ma'am.
audible, ma'am.
Ma'am,
Ma'am,
your
you are
voice
not
is
audible. Ma'am, your voice is cracking.
Voice is breaking.
Not audible, ma'am.
Ma'am, your voice is breaking.
Ma'am, you are not audible at all.
Not audible, ma'am.
Ma'am, we are not able to hear you.
That is equal to minus 1. So every single switch, the sign is changing again and again. Just one switch doesn't matter. So this switch changed the sign once. Then this again changed the sign. Okay. So this,
Ma'am,
Ma'am,
so
you
can
every,
are
you
not
please
audible till now,
repeat
ma'am.
once again? Because you are not audible.
I'm not audible. Am I audible now?
Yes,
Yes,
ma'am.
ma'am.
Okay.
But
Yes, ma'am.
Was the screen visible?
yes, ma'am. Yes, ma'am.
Okay.
Yes,
So
ma'am.
good thing. So hopefully, thing is, if I'm not audible, just stop right there because I am speaking continuously. Okay. So the thing is, every single switch that you do, so A is this, okay, we took this matrix A, we got this determinant minus 1, okay. Now we switched, the property is that switching rows or columns changes the sign, okay. So my point is, like, in these two matrices you followed, right? So here with this one, we took determinant of A is minus 3, then we switched the
Not audible, ma'am.
Ma'am, we are not able to hear you again.
Again, you are not audible, ma'am.
Not audible, ma'am.
Ma'am, you're not audible.
okay. Am I audible now?
Yes, ma'am. Yes, ma'am.
Yes,
Okay.
yes, ma'am.
Yeah. Okay. Sorry. So just someone unmute yourself because I'm sharing the screen. I can't see the chat. So that's why just someone, if I'm not audible, someone unmute and say I'm not audible. Okay. So I'll just reshare the note screen and tell me till where you followed. Okay. I did all the steps. So hopefully we won't waste too much time on this again. So I'll just go through how much ever was, like, where the audio cut out. Okay. So till here, is it clear? 1 second. The screen is now. Sorry. Okay. Is the screen visible?
Yes,
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So is this part clear? Like, we took this matrix and then this, we calculated the determinant. Okay. We switched it up and then the sign changed. So this property we proved. Okay. This stuff is where the audio cut off, right?
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yeah.
ma'am.
Okay. So what I'm saying is this, like, just builds up on this only. So the point is that, like, this is a trick question that is sometimes asked, like more of a theory, because like when we calculate it's like clear, but the thing is every time you switch the rows and columns, every single switch multiplies the determinant by, like, the sign is going to change. So first it's -1. Okay, then we switched.
Ma'am,
Okay.
audible now.
Like, I think some issue is happening, like, when I share the screen, the audio is like going off something. 1 second, let me just fix this. I'll join, like, I'll share my screen from a separate device. 1 second. Just give me one moment. Okay. Is the screen visible and am I audible?
Yes, ma'am.
Yes,
Okay,
ma'am.
fine.
Yes.
Okay, fine. So yeah, hopefully this should be okay because join from a separate device. So here, right? So the point is that every single switch that you make is going to change the sign of the determinant. So it's not like just one switch, like you can do any number of switches and the determinant is going to change signs once. Okay, so every single switch, the determinant is constantly getting multiplied by -1 or whatever. Okay, so it started with -1, then it became 1 because we switched these two. Okay, and then here again we switched this second row and third row, and then again it became -1. From 1 it became -1. So that is the point. Okay, so that is another property. And same with columns also. So let's take B and switch up the columns. So if we have B, okay, and that is equal to, so B we took as 8, 9, 3, 4. So let's take 9, 4, and then 8, 3. Okay, so first let's get determinant of B here. Okay, what is it? You tell me.
5.
5.
So 32, right? Minus 27, that is correct. Correct. So now let's just take that. And then here we have 27 minus 32 because we are doing this and this. So that is -5. So determinant of B star, okay, that is equal to -5. So that is also proven. This is the second property of determinants. So now let's go to the third property. These are really like, simple. So we'll take these two matrices only. Okay. So the third property is saying that adding multiples of a row to another row or of a column to another column leaves the determinant unchanged. Okay. So the actual property is in the lecture. So I'll just directly go to the, proof. So first let's take A only. A is 1, 2, 5, 7. Okay. 1, 2, 5, 7. So this is our A that we had. Okay. So we know the determinant of A is -3. Okay. So now we'll add multiples of the first row to the second row. So we'll make A star. Okay. So how should we do it? You tell me. So we'll take 2 times the second row and add it to the 2 times the first row because that's easier to do, and add it to the second row. Okay. So that is going to be the first row then becomes, if we're taking 2 times that, 2, 4. So we're adding 2, 4 to 5, 7. So 1, 2 is staying the same. Okay. And then we are having 2 plus 5, 7, and then 4 plus 7, 11. Okay. So now let's take determinant of A star. I'll just remove this. Now, as you can see, this is 11 minus 14, right? And this is still -3. So we can do that with the columns also. Okay. Let's take A star star. Okay. Now, what should we do? Should we take -1 times the first column and add it to the second column? Let's just do that arbitrarily. I'm just making this up, but the property is being proved, as you can see. So the first column is staying the same, and we're doing -1, -5 to 2 and 7. So 2 minus 1 is 1, and then 7, and then -7 minus 5 is 2. Okay. So now let's take this determinant. That is equal to 2 minus 5, right? And this is -3 again. Okay. So that is the third property of determinants. Clear?
Yes.
Right? Here are the 3 main properties. Okay. And also the fourth property now. Scalar multiplication of a row or column by a constant t multiplies the determinant by t. So this is actually what we also saw in this problem, right? So the first property here, and this is what we saw. So this is actually the fourth property of determinants. Okay. So scalar multiplication. So we have our A. That is, again, let's just keep it 1, 2, 5, 7, right? So now what they're saying is scalar multiplication of a row by a constant. So let's multiply the first row by 2. So now we have 2, 4, and then 5, 7. Okay. So now you can see that this gets a bit confusing because here we also scalar multiplied this row, the first row, but we added the second one. That is what we're doing, and that's why the determinant is unchanged. But if we directly change the row itself, okay, we're multiplying it by a scalar and the original row is gone, then the determinant is going to also get multiplied by that number. So determinant here is going to be what? You tell me. Of this one. So did 2 times row 1. That is what we did and we got this. So what's the new determinant?
Ma'am, -6.
Yeah, 14 minus 20, so -6. And here it was -3, right? So as you can see, because we multiplied the first row only, that's why the determinant got multiplied by 2 only. Now if we multiply the whole matrix A by 2, so if we take 2A, that is equal to 2, 4, and then 10, 14, okay? So the determinant of this is what? 28 minus 40. That is equal to -12, right? So as you can see, what happened is this new determinant of 2A is actually, because A is a 2 cross 2 matrix, so 2, this number is going to come in front, okay? And it's going to get raised by 2 and then determinant of A. And we can see that 2 raised to 2 is 4, okay? And determinant of A is what we already had, -3. So 1 second, 2 raised to 2. I wrote 4 too soon. So 4 into -3, that is equal to -12, and that is exactly what when we directly computed it also. So those are the 4 properties of determinants, okay? So another now useful computational tips that the lecture said, I'll just go over it like, verbally. It's that if there is a matrix, it has any row that is fully zeros or any column that is fully zeros, then the determinant is always 0, okay? Like you don't need to do anything. So if you have some matrix A and it's like 2, 5, 7, and then 1, 2, 3, and then 0, 0, 0. Okay. No, and they're asking the determinant. Okay, determinant of A. Directly, you will just say 0. That is a property. And similarly, if this was a full 0 column, that also you can do. Okay. And yeah, also, like if you're computing the determinant, this is like, this is what really helps students a lot. Like in exam, time is going to be, of essence. So you only have 1 hour in the first 2 quizzes, right? So if you can compute the determinant of like a matrix along any row or column. So if we have A, okay, say this is a 3 cross 3, okay. So if A is like 2, 0, 0, no, let's take it like this, 2, 0, 0, and then 8, 9, 7, 11, 15, 14. Okay, so if this is the case, now you compute it normally, you're going to take 2, okay, then you're going to compute this, then you're going to do -8, and then this determinant of this submatrix and this one. So another way to do is you can directly compute it along this. So what you can do instead, what you have to remember is this pattern of taking the signs. Okay, so you know that normally the first value we take, then the second number when we're computing, we have to take minus that, and then again plus, and then minus. So all you have to remember is this general form. Okay, so you have plus, minus, and then dot dot dot. That is going to this alternating pattern, and here minus, plus, and that continues. Okay, and here plus, and this also continues. So this is going on. So you can take any particular row or column, like you can start computing the determinant from here also, okay? And you can take this also. So what you want to do is to make your computation easier, take a row or column that has a lot of zeros, because when you have 0 and then you like it's going to get multiplied by 0, that particular sub determinant. So it's all going to go to 0. So you're saving yourself from calculations. So we'll take it along this one, okay? So now actually I'll just switch these so we can get like, the sign is clear. Okay, so now I want to compute the determinant of this. Okay, so obviously because this is 200, it's much easier to compute using this one, right? So now I just have to take care of the signs. So 2 is in the second column, first entry. So I'm setting up the determinant of it. I want to compute that. So how do I write it? Tell me like the equation. Anyone? I want to do it along the second column.
Yes, -2 from the
Yeah.
minus.
Yeah, so -2, and then as usual, what you do when you take this value, so you're taking 14 into 7, and I'm not going to do all those calculations though. Minus 15 into 11, okay? And then, because we're taking 0, now you can see here it's plus, because alternating. Once you start, you just have to know where to start. This is minus, the next one is obviously going to be plus. So it's going to be plus 0, 0, but we don't need to calculate that now because it's going to be 0 into some value and then again minus 0 into some value. So we'll just compute this. So you can use your calculator and this is going to be the determinant. So you just save, if you took this one, like if you started the normal route, then you have to do this and this, all of that. So that is another useful computational tip. Okay. So that is all we have for determinants. Next lecture is Kramer's rules. So now does anyone have any doubts in determinants?
No, ma'am.
Okay. So I'll just go
No.
to the people who have their hands raised first. Okay. Yeah. 1 second. I open the queue. Yeah, Priyanshu.
Ma'am, in one of the previous question that we solved where we had b is equal to 3a, the cube
Yeah.
root 1. So
Yeah.
there I wanted to check if it was like 4 by 4 matrix,
Mm-hmm.
so how it would change. I mean, I have doubt in this 3 raised to the 3. So what
Okay.
is
Then
the,
you would just raise it to whatever the order of the matrix is.
so it would be
So
3 raised to the 4?
4. Yeah. So you can
Okay.
take it like in general form. I'll write it down. So if you have like some matrix A, okay, it has some determinant of A is equal to suppose 4. Okay, whatever. Or let's just take some arbitrary value. Let's say DE only, small d. Okay. And now we have another matrix B, and let's say A is equal to some order. It has to be a square matrix to be able to take the determinant. That is required, right? So A is of order K into K. Okay, we don't know some number. It can be 3, 4, whatever. Okay. And then we have B that is equal to, suppose, say, whatever, 4A. Okay. So now what we have to do is just determinant of B is going to be, now because it's 4 times A, what you have to do is, actually you don't need this. Give me, yeah, 1 second. Yeah. So we'll take D here, some arbitrary value. D is a constant, okay, or we'll take C, so it's clearer, as we use C most of the time for scalars. So, and A is of order K into K. So it's a square matrix, you don't know what. It can be 14 into 14 also. And B is just C into A. Okay, so this B has the same order also. B is also K into K, right? So now determinant of A is, we'll just take it as determinant of A. It has some determinant. Okay. So now what is going to be the determinant of B? Anyone else? So we have
Ma'am,
C.
K
Yes.
C
power.
to the power k into determinant of A.
Yeah. So C, that is the number that is multiplied by A to get B. So that is still there. Now that scalar is going to be raised to the order of the matrix. So that is A. Okay. Times
Okay,
determinant of
understood.
A.
Thank you.
Yeah. Okay. So in general form, it's like clearer. So just remember this. Okay. So anyone else? Ishika.
Yes, ma'am. Ma'am, actually, I didn't understand that square root part.
Oh, the square root is just they're asking to compute this value. It's like what they're asking is they've given us this determinant of A and they're saying it's 4. And they're saying A is a 3 cross 3 matrix. They've given us
Okay, I just understood that it has some other property of determinant. Then, ma'am, this one, is it related to that? The seventh part that you have written, what is that?
Oh, this is question number 7 from activity question 1.5. So this is a separate problem. This one is, this involves the last property of determinants and also the first. So what it's saying is that we have, if just given us a real number value, determinant A is equal to 4. Okay. And they've given us A is a 3 cross 3 matrix. They have not given us the real like matrix A. They've just said it has 3 rows and 3 columns. And they've said that B, it's another matrix, and that is 3. That is what we get when we multiply every value of A by 3. So that is another matrix. And they're asking this particular value. Okay. So determinant of B is what we get. Like right now we saw this general form, right? So it's B is equal to here in this problem. So C is equal to 3. So 3A. So and because A is 3 cross 3, so 3 raised to 3 times determinant of A. So what we got is 27 into 4 they've given us. Okay. And now we just compute this value.
Okay, okay.
Yeah. And the thing is, the property that we apply, the first property of determinants, it says that determinant of A square B is like we can split out the determinant. We can take it out. So we can take it determinant of A, determinant of A, determinant of B. And this is like a real number and then third root of that.
Okay. And ma'am, one more thing. Ma'am, in the lectures, cofactors and minors were covered.
Yeah,
But
we'll do
in
that
the
also.
instructor sessions or in the team. Okay, okay.
Because
Thank you,
this is
ma'am.
the first week 2 session, na. So that cofactor comes in lecture 3, I guess, of week 2. So we'll go to that. Don't worry.
Is it, ma'am, because in the course it was in week 1 only, in the course page?
I don't know. Maybe the course structure change. I'm not sure actually, but we'll go through that. Don't worry.
Okay.
Yeah. I think determinants
That is
part
part
3
of
was
week 2.
also.
Okay.
Yeah. I think like week 1 was getting very long, so they put determinants part 3 in week 2. Something like that happened, I guess. But don't worry, we'll go through
Okay.
it.
Thank you.
Yeah. Okay. Akash.
Hello.
Yeah.
Actually, I have a doubt in activity 2.1, question number 9,
Okay,
options.
let's see that. 1 second. It's a determinant. Yeah, it's the first. Okay. Question number 9. Okay.
Option C.
Okay, I'll just share that now. I'll share the tab. 1 second. Okay, is it visible? 1 second. Yeah, is it visible now?
Yes, ma'am.
Okay, so this is like, oh, it has my parts. Okay, so here we have let A be a real 3 cross 3 matrix as given below. Okay, so here these are the columns it's saying. So like Ci represents the ith column of the matrix A. Okay, so now let us consider the following set of matrices. So A1, this is what we get when we do these like elementary operations on this A. Okay, so is this part clear? Like how
Ma'am,
this is not visible for anyone?
very well, ma'am. It's visible, ma'am.
Okay. I think just rejoin or maybe like go to the people in the meet and just pin my screen. Like your it must be showing like Arna is presenting, so just pin that. Maybe then it'll appear because it is visible, right? Okay. So here, were you able to compute the 8th part, the first sub question?
Yes, yes.
Okay. So which of the matrices have the same determinant as that of A? So what is the answer here?
1 and 2. A1 and
A1 and
A2.
yeah. So as you can see, A1 has C1. Okay, so that is the same as A, and then C2 that's same plus 5 C3, and then just C3. So the property of the determinants that we saw, okay, that adding scalar multiples of a row or column to another column leaves the determinant unchanged, right? So that is being applied here. Then A2 also has the same case because it's C1 plus C2 plus C3. So again, we're just adding scalar multiples of the other two rows to the first column, of the other two columns to the first column, right? And we're just adding scalar multiples means it's 1 times those two. So again, it's unchanged. So in the next two though, you can see this A3 has a completely separate column. It's a full 0 column, right? Because we just saw that these represent each column. So if it's saying 0 here, that means that's a whole column of zeros. So A3 is going to have determinant 0, and that is the option, this one. Okay. So it does not have the same determinant as that of A. So here we won't select A3. And A4, you can see that C1 plus C2, okay, then it won't change. And it's C2 plus C3, okay, and then C3 plus C1. Okay, so that is also happening. So,
Ma'am, in the last option, all are elementary row operation. Then
yeah.
how it is not the answer?
The
Yes.
last one, okay, let's see 1 second. Yeah. So in the last one, I guess, uh, okay, so here you are not keeping the columns same because to each one you're adding different columns. Like here, C1 is staying the same and then C2 plus 5 C3. So here everything is getting changed. You're not adding the scaled multiples of one column to another. Every single column is being fully altered. Here C1 is becoming C1 plus C2. That's okay. But C2 is also changing itself. It's becoming C2 plus C3. It's not the same C2 anymore. And again, C3 is also changing itself. So if here we had C1 plus C3, then maybe. But here and then C1 plus C3, and then here we have something else. And then, but all of the columns are changing completely because we are adding a different column to each one. So that is why this is a whole new matrix basically, and it won't have, like, these are elementary operations, but the actual matrix itself is not retaining its original form at all. Nothing is the same. So that's why the determinant is also different.
Ma'am, but we can say that column 3 is just a sum of column 3, and then in the next operation we are adding column
Okay,
1 to column
let's
3.
test this out by taking the identity matrix, what we usually do. Okay, let's try that. So we'll try the fourth option on the identity and we'll see if it. So first column is becoming C1 plus C2. Second one is C2 plus C3. Third one is C3 plus C1. Okay, so let's test it out. One second, I'm just sharing my screen. Different device, so it's taking a little longer. Just give me 1 second. Okay, let me know if it's visible. Just 1 second. Yeah. Okay. Okay. Screen is visible, right? Okay. So what we'll do now is we have A is equal to, and it's like some column C1, some column C2, some column C3. Okay. And they're saying A4 is equal to C1 plus C2, C2 plus C3, and C3 plus C1. Okay, so now let's make up a matrix A and just test. I won't take identity because then maybe we might, because they're all the same. Let's take different columns. So A is equal to, let's make up a 3 cross 3 matrix. Okay, or because there are 3 columns, yeah, let's make up a 3 cross 3 matrix. So let's take 1, 2, 0, 0, 4, 1, and anyone else? Some third row who want to provide us anything, something simple to compute also, so we can do it fast. Okay, so I'll just take 003. Okay, is that fine? So this should have a valid determinant. I hope it has a non-zero determinant. Okay, so let's compute the determinant of A first, then we'll go to A4. Okay, okay, so this is going to be 1 into 4 into 3.
12.
Yeah, 12, and then minus 1 into 0, that's I'm leaving, and then 2 into, so 2 times 3 into 0 minus 1 into 0, that's nothing, so it's all 0.
It's only 12.
Yeah, and then 0, so this is just 12. Okay, now let's make this matrix A4. Okay, so the first row we have to add the second row to it, a column, sorry. So this is going to become 3, 4, 0. Okay, now the second column we have to add the third column to it. So this is, tell me, what is this entry? The first one
5,
is
3.
5, 3. And the last column becomes
1, 1, 3.
1, 3.
113.
yes. Okay. Now let's compute the determinant. As you can see, like it's fundamentally a fully different matrix now, right? So let's compute this determinant. So 3, okay, 3 into 15 minus 3
12.
minus, yeah, minus 2 and then 12, okay, because here plus 1 and then 12 minus 5, okay.
Minus
So,
0, right?
oh yeah, sorry, 1 second.
Minus
1, 12 minus 0, yeah, sorry, okay. So here we have 3 into 12 minus 24 plus 12, right? So here we have 36 minus 24 plus 12. So this is 24. See, correct, right? Calculations are correct. I'm really bad at arithmetic, so I hope it's right. So as you saw, like not the same determinant. And here we just got 12 into 2, but that's not the case. If we took different values, it could have come like, any form. So here, that is why, because you're performing these operations on each of them and none of them are staying put, it's becoming a completely new matrix. Okay, so that is the case. That is why A4 won't have the same determinant as A. Okay, now it's proven, right? Any other doubts in 2.1?
Ma'am, the next question,
Sorry?
question 9, ma'am.
Okay.
So, ma'am, if we change only one column, then it will be same.
So here they're changing the full thing. So,
Yes.
yeah, so it's becoming a whole new matrix basically. That is the point here. So if you see the other two options here, uh, 1 second, I'll just open that. Okay, if you can see the other two options, is my screen visible? The tab is showing the question.
Yes, ma'am.
Okay, so here in the other options, you're seeing that C1 is staying the same and C3 is staying the same, and only C2 are doing some elementary operations. But here, everything is changing. So it's becoming a whole different matrix. So that's why we
So
can't.
one at a time we can do
Yeah,
that.
exactly. So that is what you have to do. So,
Okay.
yeah. Question number 9. Okay, it's a continuation of this only. So determinant
Ma'am,
of A.
yeah, sorry. My query was, ma'am, how come determinant of A4 is 2 times the determinant of A?
Yeah, that is the case here. So as you can see, we perform these row operations on all of them. So that is like, yeah, that is what we got
Yeah, we
also.
proved yes to 12,
Yeah,
24.
yeah.
Yeah,
So
that we got it with the help of an example, but I mean, before the example, it wasn't like, how
mhm,
it was a bit confusing at that time. I just noted it down.
mhm. I think like I'm not 100% sure on this also because the lectures never go into this. But even doing the example like showed it to us. But I think it may be something like because we're performing this row operation on all of them. So you know how when it's like we're doubling it in a way because every column is having another column added to it. I think that is the logic. That may be the logic. I'm not 100% sure. I'll check this up and make a discourse post maybe about it. Have to ask ma'am about this. But I think the basic logic here, because it's like that is what we got, right? We had 12, it became 24. I thought it was just, a random different solution, but this is apparently a property. So I think the logic is that because all the columns are having another column added to it. So it's like doubling basically because, um, the original determinant is just for this each column what it yields. Now you're having all the same three columns in action, but they're also being added to each other again. Now we know that the logic is that the columns, when we add another column, the determinant just itself is not the same, right? So, I mean, if we have a column and like in the example A1 for instance, so in this column 2, we're adding 5C3 and the determinant is staying the same. Okay. So now what I think is happening is we're adding each of the columns to the other columns again. So it's like, the determinant is doubling because the columns itself are still the same. So the determinant value that is yielded by these columns, that's still there, but because we have more addition to it, like we're adding it once, maybe I think this logic can be extended. If we had c1 plus c2 plus c3 and similar, then we would get something else, maybe 3 times that. So this is like, from the calculation, I think this may be the logic, but I'm not 100% sure. I'll just check with ma'am and let you guys know in the next session. And
Okay, ma'am.
yeah, this
Ma'am, question number 4 of this activity questions. I think this is the similar type of question.
okay. So yeah, this one, right?
Yes, ma'am.
So determinant of A is this matrix. So A plus B plus C is divisible by 6, and choose the correct set of options. Okay. So what it's saying, yeah. So A plus B plus C is the only, like A, B, and C are the only values that make up this matrix. Okay. So that's right. Because A plus B plus C is like those three are being used in every single, sub matrix that we use to compute the determinant. So first we're taking A and then we're doing C into B minus A square, something like that. So A, B, C are being used in every single calculation. So because A plus B plus C is divisible by 6, and they're the only values in this matrix, that's right. This determinant, because that is how we compute a determinant, right? We are adding these values only. So it's just, just logical, I guess. So because that is why the determinant is also divisible by 6, because we do like have A plus B plus C at some point, and then it's because it's divisible by 6, it's also divisible by 2. 2 and 3 are factors of 6. So that is just a very basic logic of it. No more like, just arithmetic logic. There's no more determinant property in this. Just these three values are only there. And determinant involves the computation. You are adding these values over and over. So since their sum is divisible by 6, the determinant of A involves the sum in many ways. So that's why that is also going to be divisible by 6. That's it. This
Question
Ma'am,
number
can
10
you
of the
please
same
repeat
activity.
once again this question?
Yeah. So you can take, like, in these kind of questions, it's just like, they want you to test like the arithmetic of determinants. So here, if since A, B, and C are the only values that make up this matrix, like there's also this property, right? Because you can take the determinant across any row or any column. That's also there. So only A, B, and C, you're like, you're multiplying, you're adding. So since the sum of them is divisible by 6, and they're the only three values, the determinant that you get of A, okay, that is also going to be divisible by 6. That's it. So because it's not, 6 is not divisible by 5, then that's why it's not going to be divisible by 5, unless, they also gave us more information. So this is just an arithmetic related question. This is generally not asked in the exam also. So it's just not very much into determinants, just more about how you calculate it, just basic logic. And here they've just given A, B, C, B, C, A. So just these three values only. So they're just, trying to help you strengthen the logic. It's just, determinant is just basic arithmetic only. That is it. Okay, any other doubts here?
Ma'am, question number 10 of the same activity question.
Okay. So if the diagonal entries of a 3 cross 3 lower triangular matrix A are 1, 2, and 3, then find the sum of the roots of the equation determinant of A minus x times I is equal to 0, where I is the identity matrix of order 3. Okay. So does anyone else do this? Okay. So answer is 6, correct. So how would we compute it? Can anyone share their approach in this? Anyone?
Yeah, ma'am, I took one matrix
Yeah.
and I subtract with the x.
Mm-hmm.
And then I get a matrix by 1 minus x 0 0, a
Mm-hmm.
minus x 2 minus x 0, b minus x, c minus x, 3 minus x.
Mm-hmm.
Like that, I get a equation. After
Mm-hmm.
solving that, I get x cube minus 6x square plus 11x minus 6. Then x minus 1 is the root of one equation. Then
Mm-hmm.
simplifying that, I got 6.
Okay. So let's just take this. So mm here, the thing is, one property of determinants you can see later is that if you have a lower triangular matrix or an upper triangular, so does anyone know, like, how the determinant is computed, or like, the shortcut for the determinant of a triangular
Okay,
matrix?
sum the diagonal entries.
Yeah. So just that property you remember, right? So here it's saying the diagonal entries are 1, 2, and 3. So that is the trace. A trace is the official mathematical term for the diagonal entries sum of a matrix, of any matrix. Okay. So here they're saying that 1, 2, and 3 are these diagonal entries. Okay. And it's 3 cross 3. So the trace is going to be 1 plus 2 plus 3, that is equal to 6. Now for this matrix A, we know, since it's a lower triangular matrix, for any triangular matrix, the determinant is the trace. So the determinant of A is 6. Okay, just from that. And they're saying that to find the sum of the roots of this equation, determinant of A minus x times I is equal to 0, that is given to confuse. So basically, here what you'll have is each of those like values. One, you're going to have, okay, I'll just write it out 1 second so visually we're clear 100%. Here you can either compute it out like Satara did. Okay, that is a great way. And also you can just use the matrix logic also. So I'll just do it because they're asking the roots and all that. So I'll just show you 1 second. Okay, screen is visible, right? So let's do this problem. So they've said that the diagonal entries of a 3 cross 3 lower triangular matrix A are 1, 2, and 3. So what is a lower triangular matrix? Let's begin there. So diagonal entries are 1, 2, and 3. Okay, so we know A is going to be like, it's 3 cross 3. So it's going to be 1, 2, 3. Okay, and now what is a lower triangular matrix?
The elements above the diagonal, all the elements are zero.
Yeah. So lower triangular means the lower triangle of this part that only has values. Everything else above the diagonal is zero. So the first row is 1 0 0 then, and here also we have 0. And these can be any value. So I'll take this as how we generally write it, the general form. So A21, A31, A32. Okay, some values we don't know. Just space it out. Yeah. So this is what we have, okay? And the question also is asking us to find the sum of the roots of the equation, okay? And the equation is determinant of A minus x times I is equal to 0, okay? So if you remember from maths 1, the sum of the roots, it's going to be a quadratic or some equation, and then we just have to see what x is equal to, okay? So now here we can just, if we do it manually, this is what we would do. So a minus xi, we'll take that, okay? But also this property, so property you have to remember, okay? Determinant of a, where a is some triangular matrix, okay, is sum of diagonal, 1 second, elements, which is known as the trace. Sum of diagonal elements of any matrix is called the trace, okay? So determinant of A directly, first let's get it out. We can have determinant of A is equal to, what do we have now?
6.
Yeah. Okay, so that is what we have also. And as you can see, we're taking this. We're
Is
performing
it,
A minus
so
X.
ma'am,
Yeah.
is it
The
sum of
product,
the
no, ma'am.
diagonal elements or product of the diagonal elements? Determinant of it.
Product we are
Sum of
One
doing
the
now.
second. Let me
of the
check.
diagonal.
Let me check. One second. The trace is the sum. Determinant, let me check. One second. I'll just confirm it. I think it may be
Is
product
Trace
sum
is
of
actually.
the
the
sum. Yes, ma'am. Trace is the
Yeah.
sum. With the
Is sum of
determinant
the
of
diagonal.
A will be the product.
Yeah, let me check first.
Trace is
The
the sum
trace
of
is
the
the sum
diagonals element.
of a triangular matrix. Let me just check it once. Because trace is the sum. Okay. Okay. Yeah. So determinant. One second. Determinant is the product. Trace is the sum. Product. Sorry. Okay. So this is also there. So determinant is actually, this is the trace. Sorry about that. Is equal to 6 because it's 1 plus 2 plus 3. And determinant is the product. Yeah, this is can be confusing. So it's 1 into 2 into 3, again 6 only. So that is where the confusion began. It is equal to 6. And here we have 1 into 2 into 3, 6. Okay. So it's a product though, because it was the same value and trace is also being discussed. That's why I said sum, but actually it's the product. So just remember this. I'll type up the note properly with the properties. I think you will encounter this later also. And this is trace is like very like very much used in MLF, which you'll have in diploma, machine learning foundations, linear algebra, very much used in machine learning, trace and all the determinant related stuff. Okay. So mainly trace, more than determinant, we use trace in machine learning. So anyway, determinant of any triangular matrix is the sum, is the product, is the product of the diagonal elements, which is not the trace, not trace. Okay, sum of,
Ma'am,
yeah,
ma'am, trace is the sum for every
every matrix.
matrix.
Yeah,
Okay.
every matrix. Sum of diagonal entries is always trace. That is the term for any matrix. But the determinant of some matrix, that is a triangular matrix, is the product of the diagonal elements. Okay. So here it just happened to be the same, hence the confusion, but this is the difference. Okay. So now let's compute it out manually. So let's get this matrix A minus xi. Okay, so xi, we're taking x and multiplying, because this is has to be, if we, they're saying that A minus xi has some value. Okay, that means this has to be a valid subtraction or addition with scalar multiplication. So that means I is also of order 3. So it's 1 0 0 0 1 0 0 0 1. Otherwise we just can't take A minus xi. Okay, so what this does is x 0 0 0 x 0 and then 0 0 x. Okay, and then what you have here is A minus xi. So A minus xi is equal to, so we took A's general form as this, right? So I'll just copy that and then let's bring it here. Okay, it's all visible, right? Let
Yes,
me
ma'am.
know if I'm like, audio is not clear or screen is not shared. Okay, because some net issues here. So A minus xi is what we have to do. So we got both the matrices now. Okay, so this is equal to, so 1 minus x is going to go here. Okay, and then we have 0 minus 0, that's still 0, and then 0 minus 0, that's still 0, and this part A to 1, okay, that's still there, and 2 minus x, okay, and then 0 minus 0, and then A31 is still there, whatever it is, A32, and then 3 minus x. Okay, now here's the property being applied. As you can see, this matrix is also a lower triangular matrix, right? Because the values above the main diagonal, this is the main diagonal, they're also 0. So the determinant of this matrix is going to be just the product of these three values. That is what we saw here. Okay. So determinant of some triangular matrix is the product of the diagonal elements. So the question asks determinant of a minus xi is equal to 1. That is the equation they set up. So now determinant of a minus xi is just the product of these three, right? So it is, and let's just write out the equation then. We'll write out the determinant on the left hand side and equate it to 0. So because this is also a lower triangular matrix, we'll apply the determinant property that it's the product of these three. So 1 minus x times 2 minus x, and also you can check it out, you can directly do the computation also, but what you can see is if you do it along the first row, you just take 1 minus x, do this into this minus 0, and then you won't have to do anything also. So it's being proven also. So times 3 minus x, that is equal to 0. And what the question asks is sum of the roots. So here we're getting three values of x is equal to 1, x is equal to 2, x is equal to 3, and we take the sum, that is equal to 6. So this is the general approach, and also the lower triangular properties, you can just directly apply the logic also, that is also there. Okay.
Got it, ma'am. Thank you.
Okay. From 2.1, anything else? Let's go to Kramer's rule then, because that also involves the determinant only. Okay. We'll
Ma'am,
do.
I have a one doubt in activity 2.1.
Okay, I'll take Aditya's doubt now because he's raised his hand from a long time. So if you have any other doubts, raise your hand. And after Aditya's doubt, I think we should go to the next topic because we've already spent like 1 hour and 15 minutes here. We only have till 10. So we do have a next session later this week. So in that, what we'll do is we'll properly do row reduction. Okay, and this other topic is there. That is very core topic, Gaussian elimination. So that requires a lot of time. So we won't even touch that today. Okay. So Aditya, you have any determinant related doubts? Should we go to Kramer's rule then?
Ma'am, I actually don't have any doubt, but I want to tell something that in previous lectures, sir already taught Kramer's rule, row reduction,
Yeah.
Gaussian
So
elimination, finding REF, all those. So
yeah.
it will be
So
good if you take the doubts only.
okay. So actually in PA session also we have to go through stuff. So let's go to Kramer's rule. Okay, I'll take doubts directly for that. I'll just give you a brief like the formulas that we have. Okay. And then we'll go to doubts directly. I mean, most of this part was also doubt only. So properties we do have to go over. Okay. Let's do Kramer's rule. I'll just go over the main formulas that we have for Kramer's rule. There's not much detail into it. Okay. So then we'll come to you, Radha. Okay. So I'll just do Kramer's rule quickly because we do have to do this. This is, TSN, and then we'll do some doubts. So Kramer's rule. Screen is visible, right?
Yes, ma'am.
Yeah. Okay. So what does Kramer's rule say? So this only applies to invertible matrices. Okay, that means it has to have an inverse. So they'll specify in the question if it's about a Kramer's rule. You'll learn more about invertible matrices. Like most of the next part of linear algebra is about invertibility and all that also. So this is going to only apply to invertible matrices. Okay. So if you have some like set of equations, I'll just take any set of equations. Okay. So here, suppose I'll take an example set, but first, I'll take a general form first. So if you have ax1 plus bx2 is equal to sum e, okay, and cx1 plus dx2, same x1, x2, like x and y, suppose we have, that is equal to sum f. Okay, so the Kramer's rule says that you can find these values e and f, okay, by doing some determinant computation, okay, because the matrix that we get when we take the coefficients a b c d, that has to be invertible, that is a requirement, and then we can directly compute by using the determinants. So I'll just take a real example so it's clear. Okay, so this is a very simple 2 cross 2 matrix example. Okay, so here, let's take 4x1 example. Okay, 4x1 minus 3x2 is equal to 11. Okay, and then another one we have 6x1 plus 5x2. I'm just taking it from the lecture only, is equal to 7. Okay, so A becomes, this is the coefficient matrix A. Okay, so what is the coefficient matrix? What are the values?
4 minus 4 2 minus
A,
3,
B, C, D.
6.
Yeah. So no, for this one,
4
4
minus
minus
3,
4 minus
6,
3,
5.
6, 5.
6. Yeah. Okay. So let's also write out the b, the solution part. So b is equal to this vector that is going to be 11 and 7. Okay. From we've seen that many times. So this is going to be x is equal to b form. So x is going. So this, if we write it in x is equal to b form, the matrix vector product solution form. Okay. This set of this particular system, that is going to be 4 minus 3, 6. 1 second. 6, 5, x1, x2, that is this particular x, it's not one value x, okay, and that is equal to 11, 7. So that is going to, this is b, okay. So that is this general form. Now Kramer's rule is saying, now I'll write the formula. X1 is equal to, does anyone remember? Is computing
Yes,
this
ma'am.
particular x?
Yes,
Yeah,
ma'am.
tell me.
Determinant of ax1 upon determinant of a.
Yeah, correct. Okay, and ax1 is separate matrix, we'll come to that, okay, and x2 is equal to similarly determinant of
Of
ax2.
ax2 upon determinant of a.
Yeah, okay. So now what is ax1 though? This is a different matrix, so how do we get to it?
Diagonal the column 1 by B.
Yes.
Yeah, so we will just substitute. So this is just arithmetic, and Kramer's rule is like very easy if you want to directly compute, okay, so without any cost animation, which will come to later. But the thing is, it only applies to systems like, this has to be invertible, so we'll come to that also soon. So here x, if we take ax1, let's compute that. Or first, let's compute determinant of a itself. What is it? This is the coefficient matrix A. Okay, so what is its determinant? Vidalya! Wah! 1 second. Yeah. So determinant of A itself is this one's determinant. So I'll just do it quickly. 20 minus minus
38.
38.
38, ma'am.
38.
Okay. So that is what we
38.
have. And then AX1, what is that matrix?
11 minus 3, 7 and 5.
Okay. So what we're doing is, because we're finding x1, okay, the first column corresponds with the coefficients that are on x1, right? So here we have x1 is with 4 and 6, so that is there. Now the matrix ax1, the x1 column is going to be replaced by the solution vector. So 11, 7 is what comes, okay, and the rest of A is staying the same. So minus 3, 5, okay, and this one's determinant we'll compute, okay. So that is what? What is this determinant? 55 minus minus 21. That is
76, ma'am.
yeah. Okay. So similarly, AX2, same logic. So what is going to be AX2? Anyone tell me the entries?
Yes,
Here is
ma'am.
A.
4,
4,
4,
6,
6,
11, 7.
11, 7.
Yeah.
4,
So
6,
4,
11,
6.
7.
And this thing, determinant?
11, 7.
Yeah. And what is the determinant of this one? Minus 38, I think. 28 minus 66, right?
Yes, ma'am. Minus 38.
Yes, yes.
Okay, so now let's just directly get the solution. That is all there is to Kramer's rule. So we'll just directly go to the solution now. X1, we'll get that value. That is equal to determinant of AX1 by determinant of A. So what we're doing is 76 by 38, that is equal to 2. Okay, and X2 is equal to minus 38 by 38, that is equal to minus 1. So these are the values. That is all there is to Kramer's rule. Any doubts with Kramer's rule? We won't spend too much time here because it is covered. So the general form is this. Okay, any doubts? No, right? Okay, so let's proceed to the next part, or the
Ma'am,
cofactor part. Yeah.
ma'am, please tell also the limitation of Kramer's. Why we
Eliminate.
can't take limitation of Kramer's rule? Why we can't take
Okay.
further?
So if you don't have an invertible matrix. Invertible means like in normal, like normal numbers, non-matrices, real numbers, scalars. Okay, so we have scalars. Okay, in scalars also we have inverses, right? So this is some real number C in R. Okay, so here also we have inverses. So what is an inverse in real numbers? An inverse is just you take 1 divided by that number itself, right?
Yes.
Yeah. So if I have C, the inverse of C is 1 by C, right? Screen is visible, right?
Yes, ma'am.
Okay. Yeah, Aditya, it's visible. Okay. Let me know if it's like, not visible anymore. Okay. So scalars in real numbers, we're forgetting matrices now. Okay. So when we have an inverse, that just means that we have 1 by C. And what is an inverse basically? It's when you multiply a number by its inverse, you're getting to 1. That is the property of an inverse. Okay. Now, in matrices, you can't just, like, if I have a matrix A, okay, you can't just directly take, to get its inverse, okay, you can't just take the matrix and divide every value in the matrix by, like, take 1 by every value. That is not the inverse. Okay, so in matrices, division is like not as simple. You can't just directly divide one matrix by other. So an inverse in like a minus, like raised to minus 1 is how you would say. Even here we have C raised to minus 1. That is how you denote an inverse, right? So here, inverse of A. Okay, if A is a D cross D matrix or M cross, let's take M cross M only. A is an M into N, sorry, M into M matrix. Okay, so that means same number of rows and columns. Okay, so A inverse is inverse of A. Okay, so, and what that means is when you take A inverse times A or A times A inverse, you get to I, the identity. That is the equivalent of 1 here in matrices. Okay, you can't go to 1. So the same property though, like the same, like fundamental property is still the same. Here, if we take C and then multiply it by 1 by C, we're going to 1. Okay, here in matrices, we don't have a 1. What we have is I. So the thing is, if you in matrices, if you want an inverse, then that may, if not all matrices have inverses, because to get to I, the matrices have to have the same number of rows and columns. So that is why also the determinant thing, like we have this rule. It has to be a square matrix to even have a determinant, non-zero determinant. If it's a rectangle, you can't even compute a determinant. And inverse is also like a matrix doesn't have an inverse unless it has the same number of rows and columns. So that is just key, because how will you do the matrix multiplication here? That comes into question, right? Because here, if like no rows and columns, like nothing matters. If it was A is M into N, say different rows and columns, right? So now for matrix multiplication, you have to have a specific, like, number, like, it has to be compatible. So the inverse won't be compatible with any matrix other than a square matrix. Like you just can't compute the inverse, because there comes into question, like, what if, because the inverse will switch it up. I guess if you could compute for a rectangle, then it would probably be something that you could find, when you multiply it, you get to I. But the dimensions will change again. So suppose we have A is equal to M into N, okay, and then we have some, like we get to some inverse, okay, A is to minus 1, and then that is N into M, or it could be anything, M into N. We don't know because we can't compute this. This is very hypothetical. Now, this thing, we can't get the same I again. That is what is what is happening. Because if we take A is to minus 1 times A, the A inverse times A. Okay. Now, because A inverse, let's take it N into M, and this is M into N. Okay, so now we can compute it, and this is going to give us imaginary sum N into N. Okay, now again, if we take A times A inverse, that is going to be M into N times N into M. This is also happening. Okay, but here we're getting a different I. We're getting I is M into M. So it's just logistically, it doesn't make sense. Also we could happen, like we don't even know, like if it would be yield I the same I, a lot of things. So in data, like because we use linear algebra mainly to deal with data, we don't want these irregularities. That's why this is like a key requirement. So for Kramer's rule specifically, we want invertible also. So it has to be square for it to be invertible. Like that is definitely there. Even square matrices can be non-invertible. And invertible specifically implies like this core property of determinant is that if a matrix is not invertible, like it doesn't have an A inverse such that the product is I. Okay. Then the determinant is always zero. It's always zero. So in Kramer's rule, what is happening is if the matrix A is not invertible, okay, then the determinant is going to be zero. Now you can't have zero division by zero, na? So this just won't happen. So that is that. This is the core logic of inverse. And in Kramer's rule specifically, this logic is like extended because if it's non-invertible, you won't even have a determinant. Okay, for non-square matrices, you can't compute a determinant. But if it's square, okay, if it's square, then you can compute a determinant, but it doesn't mean that it's invertible. So it could be square and non-invertible. For those specific matrices, the determinant is going to be zero. Now, if it's non-invertible, then determinant is zero. And Kramer's rule, you're applying it on non-invertible, then you're dividing by zero essentially. And that is just mathematically impossible. You cannot divide by zero. It won't mean that x1 is 0 or x2 is 0 also. So you won't get anywhere. So for Kramer's rule, they specify that because for this to be a real proper operation, to compute it like properly, the coefficient matrix A has to be invertible. That is the requirement. Because if it's not invertible, determinant is going to be 0. And this is the logic of invertibility. It's like, the what you multiply by some number to get to the one equivalent, which is I in matrices. So we'll go more into that as we do Gaussian stuff. Okay, I hope this logic is clear with everyone, na?
Yes.
Yeah.
Ma'am,
So,
hello.
yeah, Sitara. 1 second, I'll take Sitara's doubt.
Ma'am, can we find also the inverse matrix of a given matrix?
Yeah, we'll do that in the next session or maybe in the next one. We'll first have to go through the adjudicate and all that. With that, we'll use a particular method to find an inverse. But most of what we do in maths 2 is going to involve matrices, like inverse also. So Gaussian animation, which is the last concept, we won't deal with that today. That shows how to compute the inverse of any matrix, any possible matrix. And there are many
Ma'am,
ways. Yeah.
ma'am, is the adjudicate is same as the adjoint? Because in the class 12th NCERT it says
Yeah,
adjoint.
I think it's the same, only different terminology. 1 sec, I'll just check it once because in lecture I think sir also like uses the
Yes,
terms
ma'am.
interchangeably.
Sir,
Yeah.
sir has also used the terminology as a
Yeah.
adjugate, but the
Can anyone
but the
check this?
function of adjugate and the joint are same.
Okay. Let's see.
Yes, adjunct and adjoint are same.
Yeah, they're the same. So adjoint of a matrix is basically called the adjugate matrix. Same thing. It's the same. Yeah, I just confirmed it. Okay. Yeah. So don't worry, this different terminology. So in one lecture later, like there's like from week 5, like some terminology was confusing. So I had to ask ma'am directly, like, what is this? So it is confusing. So, but don't worry, it's the same only. So Kramer's rule, yes, Taya, your doubt. I'll take that.
Activity question activity 2 question number 1.
2.2 or 2.1?
Yeah, 2.2 question number 1.
Okay. I'll just share that 1 second. Okay, is it visible? 1 second, I'll stop from here. Let me know if it's visible, the question.
Yeah, ma'am, it's visible.
Okay, yeah.
Ma'am, my doubt is why the option 1 and option D. That's fourth option is correct.
Okay, so let's see. Consider a system of linear equations as follows. So it's like some general form they have given. Okay, so the matrix representation is this and this, and let AXI be the matrix obtained by replacing the. Okay, yeah. So basically, what we saw, and which of the following are true? Yeah. So 0 is the solution of every A generally. So here 0, 0, 0. If we have it, so if we have 0, 0, 0, then A it's saying is true. Yeah, so second one sec. I'll just check it. There's some technicalities here. I don't want to, confuse. Okay. Yeah, so second option is correct. Because if determinant of A is non-zero, okay, what does that mean? That means that this form AXI being obtained, that means we're applying Kramer's rule, right? So if determinant is non-zero, then that means we can apply Kramer's rule. That is there. Now determinant is non-zero, and if 0, 0, 0 is what we have, okay, then basically you have the zero equation only. Okay, and that is why it must be a solution. If you didn't have a like determinant was also zero, then we couldn't say for sure. Maybe this side was something else. But if x is equal to 0, 0, 0 solution, generally that is considered trivial solution. Okay, so what you have is in our thing, like 0, 0, 0, or like the zero vector is considered the trivial solution. So in Kramer's rule specifically, if you're getting, we like take it as a general like the trivial solution because it's always the solution. It can be a solution to anything. So here we're applying because the Kramer's rule thing is being applied because AXI they're saying. So that, and determinant is equal to AXI is equal to 0. Okay. So that means that what we're calculating is like the trivial solution because determinant of the full matrix is non-zero, right? So AXI is what you get when you like put B1, 2, 3 in place of whatever XI you have, right? So suppose this one, the first column you're making it whatever B1, B2, B3. Okay. Now you compute the determinant and that is 0. Okay. So that means that if the determinant is 0 and the original determinant of this one is non-zero, that means your computation has like b1, b2, b3 is basically a zero column because introducing that, replacing the original column with that is making the determinant 0. Previously it was non-zero, so we know this is an invertible matrix, it has a real solution. But then we replace this, then the determinant became 0. So that means that b1, b2, b3 must be zeros, right? Or you can also see it this way. B1, B2, B3 may not be 0. Okay. What you have is like you put any B1, B2, B3, suppose. Okay. Now you're getting some form and then you're calculating the determinant. Then I'll just write this down because it's really confusing just using arbitrary this. I'll just copy this and write it down. 1 second. Okay. So I'll just write down A is this general form. Okay. So it has, we'll write down the determinant of A as non-zero. It's not equal to 0. Okay. And A is just the general form. So A is like some, I'll just write instead of A11 because that will take time, I'll write 11. Or no, this causes confusion. I'll just write what it is. A sub 11 and 2 and 2, 1. So this is what they've given us A. And we got this from the original system only. Okay. So I'm not writing the whole system again, but we'll proceed from there. Okay. So we have this. Our screen is visible, right? Let me know at any point if it
Yes,
stops.
ma'am.
Okay. Yeah. So we have this. Okay. They've given us also bx is equal to x1, x2, x3. Okay. And d is equal to b1, b2. Okay, now we have everything. And this one also. They're saying the determinant of the original coefficient matrix A is not 0. That's also given to us. Okay. So AXI be the matrix obtained by replacing the ith column of the matrix A with B. Okay. So AX1, let's take for instance. Okay. So we'll just write that. So we'll take B1, B2, B3 because we're replacing the first column with this one. So then we'll take the rest to be the same. Okay. And they're saying the determinant of this one is 0. Okay. So now going back to, they're also saying that determinant of AXI is 0 for I is equal to 1 to 3. So AX2, if we take it, that also has determinant is equal to 0. Okay. So all those determinants, AX3 also is coming to 0. So I'll just keep AX1 for now. So what does that tell us basically? If the original one, just this, has determinant non-zero, but AX1 has determinant 0, and then AX2 is also having determinant 0, that means that this one is going to become B1, B2, B3, and then this is going to stay the same, and this one also. So, like, anyone would like to bring a recall some determinant property here? What is your intuition? Just tell me that. Like, what could make sense? Let's discuss. I'll just
If
write
all
it
the
out.
elements, if all the
Yeah.
elements are 0, then the determinant is 0.
Yeah. So what it's saying is like each of these is yielding a 0 determinant, but the original one is not. So that means that x1 will compute just using Kramer's rule, and because if we just directly without any determinant logic also we just apply Kramer's rule, that is also there. So we can just I'll take this whole thing again, copy. Right. Yeah, I'll put it here again. Okay. And then here I'll remove this one. Here I'll remove this one. Just keep the full question and what it's saying here. Okay, and that's saying determinant of AX2 is also 0. Determinant of AX3 is equal to 0. This is AX3. Okay, and this is the original. Okay, and this is non-zero. All right. So using just Kramer's rule, okay, because this is non-zero, we can apply Kramer's rule again. Okay. So we can take x1 is equal to 0 by some non-zero value, but it doesn't matter, determinant of A. That is equal to 0. Okay. Similarly, this is happening for all I, they said. So logically, you can compute it also. So again, using determinant properties and matrix, that also you can do. But to keep it simple, I guess, to begin with, you can do this direct computation also. So here, however, they're saying the first option in the given question is wrong because it didn't specify that determinant of A is also non-zero. Because if it wasn't non-zero, then we could never compute it actually. Here, we have each of these. Okay, we can take 0 by some non-zero value. That is a valid division, but we can't have 0 in the denominator. So they have given all of this to us. So when we take each of these, we don't need the actual determinant value because we're dividing 0 by it, right? But when we do each of these, we'll also yeah. Is it clear now? This is the logic here.
Yes, ma'am.
Okay. Yeah,
Yes, ma'am.
Ripusudan. Your hand is raised. So everyone is clear with Kramer's rule, right? And also this why we have to use invertible only. Bhavna, yeah, go ahead.
Yes, ma'am.
Oh, ma'am, is there any particular condition when to use Kramer's rule and when to use Gaussian elimination method?
So Kramer's rule you can only use with invertible matrices, but Gaussian elimination you can always use with any matrix. Like dimensions don't matter, I think. So that is a very, very basic like method. So it's going to always apply.
Ma'am, I have a
Which would
doubt
be
on
the
the
best
two.
method to prefer?
So best
More
is,
accurate.
I mean, both will yield the same result because mathematics. But unless you have like to use Kramer's rule, first of all, you have to remember the formula, and also you have to check if it's an invertible coefficient matrix. So that you have to check yourself. So you'll have to again compute a determinant of whatever you have. So instead, Gaussian is like very, very, the foundation of linear algebra, Gaussian elimination. So I would say always go to Gaussian. If you know already, if they've given all the specifics that this is an invertible coefficient matrix and it's very, just 2 cross 2 or something, very easy to compute the determinants, because this is a long calculation process, right? So that is also there. So if it's like something elementary like this, say 2 cross 2, they've said it's invertible already. Whatever is like, more time efficient in quizzes, for quizzes. But both are good to know. But in our course, Maths 2, we don't really focus on Kramer's rule after this. You have to use the Gaussian elimination over and over and over though. Because we won't always have invertible matrices. We'll have rectangular and then square but non-invertible, all that. So this has this condition, Gaussian elimination always applies. So that is there. Okay.
Okay, ma'am. Thank you, ma'am.
Yeah. Anyone else? Kramer, so we'll go to the next topic then.
Ma'am, I have a doubt on the activity 2.4, question number 10.
Help out other people, strengthen this thing, but we will come to that, don't worry. But 2.4 is actually row reduction. I don't want to get to that topic, it's very in depth. We'll do that in the next session. Today I want to cover, before ending the session, I really want to cover this one, solutions to a system of linear equations with invertible. So I want to do the adjunct, cofactor, and minors, because those are really can be a little tricky in the beginning. So I'll do that. And other activity 2.4 and all, we'll take it in the next session, or you can post on Discord, so I'll reply that. Okay. Okay, let's go to this one then.
Excuse me, ma'am.
Yeah.
Ma'am, actually, I don't have access to discourse.
Okay, one thing you can do is put your email ID in the chat. Okay, I'll just forward to ma'am. Or maybe you can search your inbox, because I think most students get it like a little later. In search your inbox, invitation to discourse, some email like that from someone, the sir called Jayakrishnan sir, Jayakrishnan YM. He's the in charge of discourse. Or maybe from IIT BS also. Just go through search your student email ID once. Maybe it's there and you didn't go, because they do send a lot of emails. Or if it's like you can't find it, you can put your email ID in the chat either way. Okay, I'll forward it to ma'am, the operations team, who can help out. But this one thing, maybe you can check, maybe you have received an invitation link, so you have to go to that. Only from that only you can access. Generally they don't let you create account directly, so look for that. Okay, and you can just
Ma'am, even I'm not receiving mails for this system.
Okay, so just put your email ID in the chat, student email ID, and then I'll forward to operations team. Okay, so let's go quickly to the solutions of linear equations. Okay, inverse. So first we already covered that, but the first concept is inverses. Okay, so inverse of a n into n. Okay, it has to be square. Okay, that is equal to a is to minus 1. Okay, that is a inverse. We call it a inverse only always. That also has the same dimensions. Okay, and this is the property that I already covered. Let's go through it for confirmation. So a times a inverse is equal to a inverse times a. Normally you won't have this, okay, but here the product, like you can take it in either order, and that is always equal to I. Okay, so this is one thing. And inverse of a matrix is unique. That is an important concept. So one matrix cannot have many inverses. Okay, so that is one thing. Okay, not all matrices are invertible. If a matrix is non-invertible, okay, then there is a term for it. Can anyone tell me? Then it is called, like, a matrix is invertible, it's called an invertible matrix. Not invertible, it's called singular. So it's called a singular matrix. Okay, and the property is this determinant of, suppose B. Okay, determinant of B is always 0. Any non-invertible matrix has determinant 0. Okay, that is there. Now what we already covered is that I'll just go through this. So here, this is like very, I'll give you the general formula, but adjugate and all that minor cofactor is going to give you the logic. But for a 2 cross 2 case, so we always have this, right? So determinant of A and A inverse. Okay, so we're multiplying determinants of these two. Okay, so we can also write this as determinant of A times A inverse, and that also means determinant of A inverse times A is always 1. Okay, so this is always there. And you can also have that determinant of the inverse is equal to 1 by determinant of A. And this is because determinant is not a matrix, it's a real number. So you remember, I introduced this concept by saying, scalars have these real numbers, and for a scalar, the inverse is like 1 by whatever value, right? So here in determinants, it's saying that the determinant of the inverse is just 1 by the determinant of the original one, because the determinant is a real number value. It's a scalar, right? That concept is clear, right? So you can see how it's relating to the arithmetic part, right? So yeah, Vinash, any doubt here?
Ma'am, I'm saying that how can we say by looking at a matrix that it is invertible or singular?
Okay, so by looking at it, if it's non-square, if it's like, not same number of rows or columns, immediately you can say it's singular. Okay, but if it is square, then you can compute the determinant, and if it's 0, then it's definitely not invertible. And then, yeah. Yeah, Ripusudan, you still have your hand raised. Any doubt? Yeah, 1 second, I'll come to you. The
Ma'am, can
same.
you please tell how to check the invertible and not invertible matrix?
Okay, so if you have a rectangular matrix, that means non-square, okay, it's definitely not invertible. It has to be square to even be invertible, even, but if it's square, that doesn't mean it's definitely invertible. So if it's square, then you can compute the determinant, because you can't compute the determinant of rectangular matrices, right? So then if the determinant that you compute of this given square matrix, that is 0, then again it's not invertible. Okay, and then if it's non-zero, then it's invertible.
Okay, ma'am.
Yeah. And another thing is, if a matrix, like another column or row, is a scalar multiple of another row, okay, then it's going to have, it's not invertible. Basically, you don't want linearly dependent. This is a very core concept. It's going to come in week 3. A lot of this you're going to hear. So that means when one row or column is like a scalar multiple of another in a matrix, not for determinant, just in the matrix, you have one column, say 100. Next column is, or say one row is 100, top row is 100. Okay. And then the next one is again 200. So this is just 2 times the first row, right? So even if this is like 7, 8, 9 or something, the determinant is going to be 0, because this is, and this is not invertible. So if determinant is 0 of a matrix, that means it's definitely not invertible. So that is a check. Okay. And now here's a formula that may come in handy, because it's like for 2 cross 2, you can directly get it, but it also uses the adjunct part, which we're going to come to. Okay. So for a 2 cross 2 matrix, for A, that is 2 cross 2, okay, So suppose A is equal to A, B, C, D. Okay, you can directly get the inverse now. I'll just give you this. So A inverse, this is, I don't think this was like, mentioned in the lecture, but this is like a shortcut. So I don't, maybe it was mentioned, I'm not sure. But because everyone wants to know directly how to compute the inverse, so this is like a shortcut you can use. That is going to be equal to 1 by, so this is a real number scalar, okay, determinant of A, times, now you're going to switch up this matrix here. Okay, so what, instead of A, what you're going to take is you're going to switch up A and B.
D.
A, and then minus B, and then minus C. So yeah, so yeah, this was in the lecture, right? It was added later, I think. Either way, so this is how you would compute it. This is a very, for only 2 cross 2, for like this general formula, obviously. It also builds up on the adjugate part, okay? So you can, but that is a more general form. For 2 cross 2, if you quickly want to get an inverse, you can do this, okay? So this is there. So again, you have to have a square matrix because otherwise you can't compute the determinant, and the determinant has to be non-zero because you're dividing by the determinant here. That is a scalar you're multiplying. And you have to switch up the values here. So these two get interchanged and these two each get multiplied by -1. Okay. So this is there. Now let's go to adjugate of a square matrix. You can only take it for a square matrix. Okay. So we'll start with minor first. Okay, we don't have much time left. I'll do minor, cofactor matrix, and then this is the adjugate part. Okay, and I don't know, I have taken a screenshot of all of those people who gave their email ID, so I'll just forward it after the session to the operations team for discourse access. Okay, if anyone else also requires discourse access, you can put it in the chat. At the end I'll forward it. Okay, so now we'll do minor. So let's go quickly. So what is the minor? So the ijth minor, so we saw ijth value, right? The ijth entry. So ijth minor of a matrix, what is it? So I'll just write the title, adjugate of a square matrix. Okay, so now we have minor. Okay, so ijth minor is what? Of a matrix. So how would we compute that? So let's bring back the general form again. So I'll just use this one only because it's very convenient. We have this A. Okay, this is our A. Okay, now
Excuse me, ma'am.
I, yeah.
Ma'am, this adjugate of a square matrix is valid for 3 by 3 matrix.
Or 4 by 4, any square. Yeah. This is also like this, like whole logic is how we get to this particular formula. You're using the adjugate logic only.
Okay, so it's not valid for 2 cross 2. Rest all the square matrices.
No, it's valid for 2 cross 2 also. By
2 cross.
using the 2 cross 2 form, we got to this general formula that you can quickly use.
But in 2
this
cross
will,
2, we cannot take out the minors and all, no?
in that you would directly go to like the first one. It's like you can directly go to this computation only. That is what is happening. We'll go through an example, don't worry. Yeah. So let's see. What is the ijth minor? So suppose we have 1 1, the 1 1th entry. Okay, so mij is what? Anyone? M11, I mean.
822 into 833 minus 8 into 823.
823 multiplied by 832.
I didn't get that. 1 second. So all of these people don't. Yeah. So it is the determinant. Like, what is it basically? For like in words.
Determinant of A22, A23, A32, A33 with the positive sign.
Yeah. So basically, it is the determinant of the matrix that we get when we remove this like A11. So we're taking so all we're removing the corresponding column and row. The matrix that remains, we're taking the determinant of that, right? And that is the ijth minor. Okay, so here what we'll have is in this general form, we'll get some minor. Okay. So let's take a real matrix. Okay, just give me any matrix again. A 3 cross 3.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Uh, I don't think this will work because I'm not sure if this is, I think this is not invertible. So I'll take something different. 1 second. Let's take 101, something easy to compute also. 101, and then 010, and then let's take 3, 2, 7. Yeah, okay. So what is the 1/1th minor here? M11. Or let's take M23 for simple, for like, understanding it better. M3. Okay. So that is the determinant. Okay. So now let's write the matrix that comes when the matrix that we have to take the determinant of. So what is the matrix here that we're finding the determinant for? 2,
0,
3.
1032.
Okay. So 2, 3 is basically which entry? It's this one, right?
1032.
So we're
Second to third
removing
row.
this one and this one, right? These two we're removing. So what we have is
1032.
3, 2, right? Okay. And now the determinant is -1. Okay. So that is basically the logic of minors. Now the ijth cofactor is defined as
Ma'am, it will be -2, no?
Yes, please.
Sorry, 2.
2. Oh yeah, sorry. Correct. For some reason I thought the 0 was 1. So 2 into 2. Okay. So that is that. So now the ijth cofactor is defined as Cij into -1 raised to I plus j into
Ma'am, you are not audible.
Not audible, ma'am.
Yeah, 1337. Yes, ma'am.
yeah. 1 second, guys. My net went off. 1 second. Am I audible now?
Yes, ma'am.
Yeah.
Yes,
Yes,
yes.
ma'am.
Yeah. Just some net issue here to defy. Yeah. Okay. Hmm. Screen is visible, right?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay. So Cij is -1 raised to whatever ij you have, that you have to take I plus j. Okay, so this is going to vary based on whatever entry you have. Okay, so sometimes you're multiplying by -1 or not -1, because if it's an even number I plus j, then it's going to be 1 again. It's the sign is going to stay put. And if it's going to be like I plus j is a non-even number, then you are multiplying mij, the minor, by some -1. So sign is getting flipped. But this is like Cij, this is how you compute it. So it's going to vary based on each other. So for M23, if we calculate C23, okay, that is going to be what? You tell me. -1 raised to what? We'll write out the full form.
2 raised to power 5.
Yeah. And then this is coming to 2. Okay. So -1 raised to 5, it's an odd number, it's still -1. So -2 is the answer. So now cofactor matrix C is what you get when you each value of the matrix. So because this is 3 into 3, so 3 cross 3, you have 1, 1, 1, 2, and 3. So you will have this whole matrix, and each value is what you get when you compute, this ijth cofactor. So a matrix made of that. C is equal to C11, C12, C13, dot, 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 C33. Okay, so that is what you get. Okay, so that is, and now I hope because minor and cofactor is clear, you just have to do it for every single value in the matrix that you have, then you will get the cofactor matrix. Okay, so I won't do the full computation because we have to get to adjugate. That is the main part. So the adjugate matrix. Okay. So does anyone remember how we get the adjugate from this cofactor matrix?
Ma'am, we take the transpose of
Yeah.
cofactor.
And what is the transpose? Like what are we doing?
When we arrange the
Row to
columns.
column and column to row.
Yeah, correct. So that is just C transpose. Okay. Now the adjugate, okay, the determinant of the adjugate is, this is the property. Okay. So determinant of adjugate of A. Okay, that is the matrix you got when you took the transpose of the cofactor matrix. That is equal to determinant of the original matrix A. One second. Okay, and then you raise it to n minus 1, where n is the order of the matrix A. So here A is 3 cross 3. So what we'll do is we'll just take determinant of A. And what is it being raised to here? For this particular A, 3 is n, right? So we'll just square, right? That's done. From here, all you have to do, this is a real number. Yeah. Okay. So this is how you would compute it. So now, finally, the inverse. So this is just a property of, like, the adjugate. The main thing you have to remember is the adjugate matrix of A is equal to C transpose, and that's written as ADJ in brackets A. So I'll put this in the top page only, so we have everything here. Not this. 1 second. Yeah. Okay. So that is denoted as this. So this is just a property of adjugate, that if you want to compute the determinant of the adjugate, then you take this. So for our particular example, because 3 cross 3 is going to be whatever the determinant is. So of that raised to 2. So here, let's do it for our example. We don't even need to compute, all the cofactor and all that. So let's just directly find the determinant. Okay. So here, what do we have? 1 second. Okay. So here, determinant of A, let's find that. What is it of this particular matrix? This one. Okay, so we have 1 into 7 times 1 minus 0. So we have 7 here. Okay, and then it's 0 plus 1 into this part. So 2 into 0 is 0 minus 3. Sorry. So 0 minus 3. Okay, so that is 4. So now, directly without computing the cofactor and all that, we can directly find the determinant of the adjugate matrix. We don't even need the adjugate matrix. That is going to be this thing, determinant of A squared, right? For this particular case. So here, that is going to be what? 4 squared, because we got 4. So that is equal to 4 squared. That's equal to 16. For our particular example. Okay, now finally the inverse computation. Okay, this is what you have to remember, and we'll end the session on this note. I'll take 2 more assignment question doubts. Okay, but we'll do row reduction and Gaussian only. We'll focus on that because very core concept in the next session. All right, so A inverse is equal to, this is a very, you won't use it as much actually, because we will always focus on Gaussian elimination, but it's good to know in the beginning, okay, because we do discuss invertibility and all that. So A inverse is equal to 1 by determinant of A, that is the original matrix, times the adjugate matrix, whatever you get. Okay, this is the formula that you'll use quickly to compute the inverse. Okay, so that is all for today. All right. So, and also to find the solution of a system of linear equations, quickly that final part I'll also do. So Ax is equal to B is the matrix vector product representation of like a system. Okay. So to find x is what we want to find, okay, for any dimension. So we could have x and y, or maybe we have x1, x2, x3, 3, x, y, z, however you want to find. Okay. So this is like some system. Okay. We don't need the technicalities, but you can directly find the solution using the inverse of the coefficient matrix. So this way, if it has, the coefficient matrix has an inverse, then you can use this method to find the solutions. Otherwise, generally you would go to Gaussian. Okay, so what happens is you take A inverse, then you multiply each side of this equation by A inverse. So I'm just multiplying A inverse on each side. Okay, so that is doable. You have like still a valid, equation. We're just multiplying each side by A inverse. Okay, then because this is the inverse of A, the product here, what does this become?
I.
Yeah, so this becomes I times X, that is equal to A inverse times B. Okay, and I into anything is just the itself because it's identity. It's like one equivalent, so that is just A inverse times B. So if you have the inverse or you computed it, then to find the solution, all you have to do is multiply the inverse by whatever RHS you have of the system. Okay, that you would put in a vector B as you see before, and that is just the solution in this case. Okay, so that is all for a day. Any other? Oh yeah, Aditya, I'll take your doubt now.
Sorry, ma'am, mistakenly I raised.
Okay. Um. Yeah, Aditya Pudel.
Yes, ma'am.
Yeah. Any doubt? Your hand is
Uh,
raised.
yeah, ma'am. Practice assignment one, question number two.
One. Okay, let's go to that. But I think there is going to be a deadline set for this, and also um, it covers mostly week one. Let's see it. Okay, 1 second.
Ma'am, the deadline says 24 March.
Yeah, that is an error actually. But I'll just give you an overview of this question. Okay, no worries.
Yes, ma'am. Just the option D, fourth option.
Yeah. Okay, let's do that. 1 second. I'll share that screen now. Okay. Is it visible?
Yes, ma'am.
Question number 2.
Yes, ma'am.
Yeah. Oh yeah, I think we went through this in the first session itself. The number of scalar additions to be done to compute the matrix AB, where A is 3 into 2 and 3 cross 2 matrix and B is 2 cross 3 matrix is 9. Okay, so what is happening is you're computing AB. Okay, so now the product AB, okay, what is its dimension, order?
3 by 3.
Yeah, right. So 3 by 3. So how many entries does it have total?
9.
9. So when you're doing the computations, you are computing like each, scale, adding the real numbers, the scalars, the addition of the scalars for each of those 9 entries, right? That is what is like they've put it in a more, theoretical way, but
Ma'am, the
that.
last part I didn't get.
So you're doing the computation, you're calculating the product, right? Of A is 3 into 3 by 3 cross 2 and B is 2 cross 3. So the AB is 3 cross 3. That means it has 9 entries. So for each of those 9 entries, you're doing like, you're taking like to compute the matrix, the product, you're doing 9 separate calculations of real numbers, right? Which is scalar additions.
Ma'am,
That is.
still I can't get you.
Could anyone else put it more simply than this? Like anyone
Ma'am,
else have some analogy? Because
if you could demonstrate it, it will be more helpful, I guess.
okay, let's do that. I'll just take the simple identity. Okay, we'll do that. Okay. So you have A is 3 cross 2, right? So I'll just take some 3 cross 2. So it's going to be like, let's say 1, 0, 2, 3, 4, 5. Oh no, I'll take something simpler. 1, 8 or 1, 4 only. Okay, B is 2 cross 3. So now that means 2 rows and 3 columns. So we'll take something else. So we'll take 1, 0, 1, and then 0, 2, 3. Okay. Now we're taking AB. So this is 3 cross 2. This is 2 cross 3. Okay, we can do AB. So AB we're computing, right? So we take this one, 1, 0, 2, 3, 1, 4. And then we have 1, 0, 1, 0, 2, 3. Okay. Now to get this is going to be 3 cross 3, right? Because these two have to be the same for a valid multiplication, and the product has 3 cross 3, right? Now,
Yes,
how do
ma'am.
we multiply? How do you multiply? You tell me this. What is going to be the first entry?
One, yeah,
Okay.
one itself.
Yeah, 1 plus 0 because we do 1 into 1 and then 0. Okay. What's the second entry?
Uh,
Yeah.
Zero.
Yeah, someone said 0. So what is happening is you're taking one, the first row. First, you have to take the first row and deal with each column. Okay. So first you took 1 into 1 and 0 into 0 plus 0 into 0. Okay, so that is just 1. Then you're taking 1 into 0 plus 0 into 2. That's just 0. Okay. Then what is the third entry then?
One.
Yeah. So that is just 1 into 1 plus 0 into 3. That's just 1. Okay. Second. So what is this entry going to be? The 1st entry. Anyone?
Two.
So it's 2 into
Two.
1 plus 3 into 0. Right? So that is there. Now the next one.
6.
6.
6.
Okay. Then we have 2 into 1 plus 3 into 3. What is that?
11.
Yeah. Then
1.
1.
and then
Next will be 8.
1 into 1 plus 4 into 3.
13.
So how many calculations did we do here?
9.
Yeah.
Okay.
Yeah.
Okay, ma'am, got it.
Yeah. So that is it. Okay.
Yes.
Everyone is here. So next session we'll properly go into row reduction. That is very good. And till then, if you have any doubts, you're ahead. You can post on Discord. We'll reply. We'll keep an eye on other students. Okay. So we'll end the session here for today because it's already 10:17. All right,
Thank you,
everyone.
ma'am.
Thank you so much for joining.
Hello, ma'am.
Yeah.
Is there any other shorter way for finding the inverse of a matrix?
Gaussian is the main one, and what we saw is like, what Gaussian is like, once you know what to do, it's going to be very easy. But getting into it, like first, introduction is going to be a little, it has a lot. It's a bunch of steps, but once you do it over and over, that is the method you're going to go to. That is the most fundamental. It's going to work for all matrices. So we'll do that only going forward. But the methods that are discussed here are the only ways. So whatever works for you. You saw this session, whatever takes less time or whatever formula is easier for you to remember, that you can do. Okay?
Okay.
Okay. All right.
And one more query was practice assignment week 1 solutions. When will we get them?
I think the deadline actually, the Instagram Lavanya ma'am and I, like we have asked the operations team to like put it, like generally practice assignments have a deadline a few days before the graded one for maths too, because you solve that and then like the solution gives you like a very nice way to solve the graded assignment. Okay. So, but right now, for some reason, this one's deadline is like 24th March. So as soon as that is sorted, I think the solution will be posted, or it's going to be posted in like by tomorrow, hopefully, because graded also is there. So we're trying to sort this out, hopefully soon, like before week 3. Okay.
Okay.
All right, everyone. Thank you so much.
Thank you so much.
Yeah.
Thank you, ma'am.
Good night, ma'am.
Good night.